Welcome to the second part of Chapter 12, Lecture 2. Uh, we're going to look at 11 different practice problems that involve information that we've covered in Chapter 12, Organometallic compounds. So let's look at the first problem. Which of the following solvents is or are suitable for the preparation of a Grignard reagent? And you can see hexane is A, B is tetrahydrofuran, C is ethanol, D ethyl ether, and E is B and D. Let's pause for a moment. You might want to pause the podcast for a second and determine what you think the answer is. Okay, let's go ahead and look at the answer. Okay, D and B are correct. Which of the following solvents is suitable for Grignard reagent? Tetrahydrofuran, of course, is THF, and ethyl ether is just a common name for diethyl ether. And the Grignard reagent is prepared by adding an alkyl halide to magnesium shavings being stirred in ether, which is known as diethyl ether, or tetrahydrofuran. We've seen reactions of bromine attached to a ring structure or bromine attached to an sp2 carbon in a straight chain hydrocarbon. And in the presence of magnesium with diethyl ether or THF, we can insert the magnesium atom between the carbon and the bromine, forming the Grignard reagent. So only B and D are correct. Okay, let's go to the second problem. Which halide is most often used to prepare a Grignard reagent? Okay, let's pause and again select what you believe is the best answer. Okay, we're back. Now the answer should be C, bromine. Okay, alkyl bromides are most often used because they react more readily than alkyl chlorides and are less expensive than alkyl iodides. Alkyl fluorides do not react. And in fact, we have seen only bromine used to prepare Grignard reagents in any of the examples that we've studied so far. Of course, iodine is at the bottom of near the bottom of the family of halogens, then bromine, then chlorine, then fluorine at the top. Fluorine, chlorine bond quite strongly with carbons, making them less easy to remove or rearrange as we do in the Grignard reagent. So bromine is right there, not very expensive. So it is the best answer. Let's go to number 3. What is the product of the following reaction? So let's pause for a second. Okay, here is the answer to number 3. What is the product of this reaction? Okay, taking a look at it, you'll notice that we have in step 1, we can create the Grignard reagent with this combination. So now we know that we're going to have a Grignard reaction type mechanism going on here. So the Grignard reagent at nucleophile and our MGBR or carbon forms first, which then reacts with the proton from the water, which is electrophilic. This is formally a reduction reaction, and THF is the only solvent. So again, here we've got a nucleophilic component, and after magnesium is inserted between the carbon and the bromine, it's even more nucleophilic. And HOH or H2O, that's here, the proton on HOH, or the proton on the water, is electrophilic. So we're going to get a replacement of the bromine with a hydrogen in a reduction reaction forming this product, D. Okay, here is number 4. Take a look at this for a moment. Pause. Okay, let's look at this reaction, and the answer should be C. Notice nucleophilic ring opening of epoxides occurs at the least hindered carbon. So, we've got the Grignard reagent right here formed, and this is a very nucleophilic carbon due to the magnesium bromide bonded right to it. So that's very nucleophilic, and it's going to go for one of these carbons that are bonded to the oxygen forming this ring. And this one right here is the least hindered of the two. Therefore, that's where the carbon is going to where the nucleophilic attack will occur. These electrons will go back up on oxygen, forming an intermediate where we now have the double bond on the end of the molecule, as you can see here. There'll be a negative charge on the oxygen initially until we provide a proton from the hydronium ion, forming the final product. Okay, let's look at the fifth example, the fifth practice problem. What is the major product of the reaction shown here? Now, this is quite similar to number 4, but take a look at this, and then we'll look at the correct answer. C should be the correct answer. Notice we have the Gilman reagent. There'll be 2 of these alkene-like structures bonded to the copper lithium. This is an organocuprate, and of course, again, it is the Gilman reagent, and it's going to be a very similar kind of reaction as we saw earlier with the Grignard reagent. This is going to be very nucleophilic, this carbon right there, and the site on this ring, both of these are electrophilic, but again, it will go for it says nucleophilic ring opening of epoxides occurs at the least hindered carbon. That is the carbon that doesn't have an R group. This is a methyl group attached. So we will form this product. Again, we form initially an intermediate with oxygen that has a negative charge on it, and then through the hydronium ion, a proton is provided and it becomes protonated. So we form this product, C. All right, let's look at problem number 6. Which of the following compounds was named after Henry Gilman? Okay, we just finished looking at the Gilman reagent. So this one should be pretty easy. Let's pause for a second. Okay, here is the answer, B. Again, Gilman was a organocuprate type reagent, copper lithium, and all of these are other reactions, and we didn't cover the still reaction. That is also a coupling reaction using this reagent with that atom in the middle right there. Okay, let's go now to the 7th practice problem. The following reaction is an example of what type of reaction? So let's look at this. Pause for a second. Here it is. Of course, this is the Suzuki reaction. You can see that readily. You'll see the palladium catalyst prominently displayed and a base. And we have a nucleophilic compound right here. In fact, this is the reactant, and this is the electrophile right here, and a leaving group iodine. So the Suzuki reaction is based upon reaction of an organoborane compound with an alkenyl and a real electrophile. So this is an aryl electrophile, and here is the organoborane structure that we see in the Suzuki reaction along with the palladium catalyst, the organoborane combination that we see here with Suzuki. So let's go now to practice problem number 8. What type of reaction could be most easily used to accomplish the following? So take a look at that for a second. C, the Heck reaction. Here we see in this problem, here is an aryl halide, and of course here is an alkene. Notice this is a terminal alkene, which is a good reactant in the Heck reaction. And it doesn't give the intermediates, or not the intermediate, but the reagents here course, we're going to use a palladium catalyst and a base, and we'll form this product. Notice it's trans, which we have seen before. So a Heck reaction couples in a real halide with an alkene in the presence of a base and a palladium catalyst. Of course, we've got the halide, the aryl halide, and the alkene. The R group of the halide replaces a vanillic hydrogen of an alkene. Of course, this is the R group, and this is the vanillic carbon with the vanillic hydrogens. The new carbon-carbon bond joins two sp2 carbons that we see here. The others would have different reagents that would result in a different kind of product, so we know it's going to be the Heck reaction based on the two reactants that we see and the product that actually remains trans in its stereochemistry. That's another hint that it is Heck. Okay, here's number 9. What type of reaction could not be used to accomplish the following? Take a look at that. Okay, let's look at the next slide. The Grignard reagent is the one that could not be used. Gilman, Heck, Suzuki reactions always couple an aryl, benzyl, or vinyl halide with its particular reagent. The halogen, in this case bromine, is the leaving group. Now with the Grignard reagent, which already has magnesium bromine in its structure, it reacts with another electrophilic carbon in the molecule. The Grignard reagent has the leaving group, which is containing magnesium bromide. So it doesn't, it's not going to go for, it's going to go, in this case, as you can see on the slide, the Grignard reagent would react with the carbonyl group, not the halide, as you can see. So let's go to the next slide. Here is problem number 10. Name the following reaction type. Of course, it's listing A through E. So take a moment to look at that. Here it is. Name the following reaction type. We've got Gilman, Grignard, Heck, and Suzuki. And the Grubbs metathesis actually is the correct answer. Now you'll notice in this reaction, it didn't show it to us on the previous question. If it had shown the ethene product, it would be a complete giveaway as the Grubbs metathesis. But if you were to look at this starting material and the product, you realize that there is the need for a 2-carbon segment, because if you gain a bond here, we still have these 2 carbons to deal with, and you would know that it is the ethene that would tell us that it must be the metathesis reaction. Gilman, the Grignard, Heck, and Suzuki would result in a different kind of product. All right, so there it is. Let's look at the last one. Which of the following would be an unlikely final product of a metathesis reaction? Let's pause. Okay, here is the answer. As you can see, it says which of the following would be an unlikely final product of a metathesis reaction. Now you may remember that a metathesis reaction is going to involve at least a terminal alkene. And this is a terminal alkene, so it's more likely to be a reactant in the metathesis reaction than it could not be a product of the metathesis reaction. A, B, C, and E could be rejoined fragments that occur in the metathesis reaction. They do not have any terminal double bonds present in any of these. So the best answer would be D. Okay, that concludes our discussion of these 11 problems.